Welcome to Computer Architecture. In this mini lecture, we are going to talk about different types of operations, in particular, logical operations and operations that we can use to make decisions. What's logical operations? Operations work on the field of bits or even individual bits. And two common ones are shift left and shift right. And if you recall, there are one field in the representation of the MIPS code or MIPS operation, which is shift amount. Then that's where we can specify the amount of bits that we want to shift left or shift right. Then in terms of arithmetics, what does shift left mean? That's one question that you should know at this point. Then there are three types of logical simple operation. It's a bit by bit and AND operation, and bit by bit OR operation, and bit by bit NOT operation. And one interesting thing that's implement inside MIPS is that it actually implement a no operation. And the reason is that MIPS want to keep up with the three operand format. But if you think about it, for NOT, there are no three operands, right? And then remember, for operations, we can also have this constant field. So for logical operations, it's the same. We have N immediate, so NI, and O immediate or OI. And for no, there's no immediate version because there's no notion of using constant in the no operation. Then with the understanding of these different operations, one very common trick that we can do is to isolate a certain field in the word. So word is a group of bits, okay? So let's think about it. What type of operation, which logical operation that we can use to achieve this purpose. Then the other type of operation that we want to do is to make decisions, or more precisely, we want to do conditional branches. When writing program, it's very useful if we can decide which instruction to be executed based on the input data and then based on the value created by previous computation. And a concrete example in high-level language is the if statement, okay? Then one common MIPS operation is called BEQ, register 1, register 2, L1, where the name of this BEQ is branch if equal. And then L1 is the label inside your code, which means that label points to a certain instruction. So the pseudocode for this instruction is that if the value inside register 1 is equal to the value inside register 2, then you can jump to the instruction that has the label L1. So that's what it called branch if equal. If it's not equal, then it keeps executing. Then a similar concept is a branch if not equal. So the format is the same. The only difference is that the comparison here is different because it's not equal, then I need to jump. And if the two values are equal and I don't jump, I keep executing the code in the next one. Now with these two operations, then you should ask yourself the question, how do I achieve if then else, right? That's in terms of high-level language, that's what we are comfortable with, what we know. But like an underlying, there's no notion of if then else in MIPS architecture, in MIPS assembly language. What you have is that branch if equal and branch if not equal. Then another common usage is that when you have a for loop or when you have while loop, you can also use these two conditional branch operations to achieve that. So how do we achieve it? Then another important concept, when talking about conditional branch is that, remember, in this von Neumann architecture or the store program concept, all the instructions are stored inside memory sequentially. And then when we're doing the computation, when we're doing the execution, we execute them one by one, unless we have the conditional branch. So in terms of mental concept, a sequence of instruction or sequence of lines of code such that there's no branches, except maybe at the end that we are going to jump, and then there's no branch target or branch label with inside the block. It's at maybe at the very beginning. So that block or that sequence of code is called a basic block. And this concept will be important later when we do a more complicated analysis. And then another very important operation that are useful for making decision is called set on less than. So the format is like this: SLT, set on less than, and then register T0, register S3, register S4. So the meaning of this instruction is that I'm going to compare the value inside S3 and then S4. So I'm going to turn on the value of T0 if the value inside S3 is strictly less than value inside S4. Okay? And then as you can imagine, this is very useful when we want to check and compare the values. Okay? And then there's also the immediate field, because maybe I don't know what's inside S4. I know that, okay, I want to run a for loop for 10 times or something. Then I can specify that here using a constant. So at set on less than immediate is identical, except that the variable here, which becomes a constant, is a 10. If S2 is strictly less than 10, and I'm going to turn on or set on the value stored inside T0. Then remember that in terms of numbers, binary numbers, we have signed version and unsigned version. Then when we do this, we also have the unsigned version, which just add this U to specify that when we are doing the comparison, the numbers are unsigned. And one interesting application of this is that we can check this condition very efficiently, where X and Y are two variables. And then if you write a lot of code, you will immediately recognize that this kind of condition is very useful when you write a for loop. And one key observation before I tell you the trick is that, remember in 2's complement notation of binary numbers, that if the number is a negative integer, then actually when we do that in the unsigned notation, it becomes a very large number. And then if you don't follow this key observation, make sure you go back to check what does 2's complement mean, and then you will understand this observation. And then starting from this observation, one implication is that if we want to compare X and Y, right? And then if both of them are signed number, but somehow when we specify this, the comparison is an unsigned comparison, then we can check two conditions at the same time. And that's very useful for determining whether it's out of bound when we are doing array or doing a for loop. The first one is that if X is negative, and then the second one is the nominal one, meaning that whether X is strictly less than Y. And later on, we will see that why this can be done efficiently. And the final thing we want to do is that when we are writing tons of code, sometimes a simple if then else is not enough. We might want to have a switch cases, a case statement, and there are two methods to achieve that. The first one is that we can do a sequence of conditional tests Intuitively, that means that we are going to have a chain of if, then else. Then the method 2, that's cleaner, is that we can have a table that store the address that we want to jump to. And more precisely is that when we have a switch case, is that okay, I check the variable, and if it match this case, I'm going to jump to that instruction. If it match the other case, I'm going to jump to the other instruction. And those jump or the destination address can be specified inside the jump table. Then what it does is that when the program executes this switch cases comparison, it will load the entry from the table into a register, and then there's a special instruction in MIPS called jump register, JR, that can jump directly to the intended label that was loaded from the table. And then this way it's much more efficient, much cleaner to implement. And that's all.